try to answer how easy or hard it is to port a mature application to a Summit-like node, how the Power 9 CPUs compare to other types of CPU, mostly Intel CPUs, for specific application, what the Volta GPUs add to the mix, and when you take the whole node, how this compare to other nodes on other leadership systems. We are very big consumer of compute power, so leadership or nothing, pretty much. So this is will be small scale test because we have only a limited hardware, but we try to extrapolate from there. And I'll try to tell you a little bit more what we do. So how it was started? Well, General Atomics decided to go ahead and buy some Summit-like nodes in early 2018. We were told we were the first people outside ORNL to get our hands on nodes like that. We didn't get exactly the same nodes, but we tried to get as close as possible to what would be delivered, because still confidential at the time. And all you know now, Summit is #1, but at that time it was, well, it will happen eventually. And then we went ahead and ported and benchmarked CGYRO to the new nodes, with the objective being to identify and solve any issues well before our user hit the real system, because we want them to get in the moment allocation is given to them, get in and run as fast as they can. So, who are we? Well, General Atomics is a private held company that does a lot of stuff. This in particular is our magnetic fusion energy division. And we are leaders both in the US and worldwide in fusion energy research. We operate the D3D device, which I'll talk a little bit more about later. We have a prestigious group, theory and computational physics group, but we collaborate with the fusion community all over the place. And we're aiming at fusion as clean, practical source of electricity. That's what is our driving force. So, just a big picture slide of General Atomics. We're located in San Diego and have been around for a long time. It was founded in 1955 as part of General Dynamics, then changed name multiple times, but we are still pretty much the same company. And have been doing fusion research pretty much from the start. So we have been 50 years in this business. And I'm told I'm not a physicist and I haven't been around that long, but they claim that even though we have been working on fusion more than 50 years, and that seems a long time to do something, the energy output from fusion has grown faster than the Moore's law since then. So we're doing good. And do all kinds of stuff, including in high technology research, design, manufacturing, both for industry and governments. So a little bit about D3D. Well, this is the tokamak that's the fusion that sits in, not exactly in our basement, but in our complex. It's not that huge, as you can see, but it's still the biggest tokamak available in the US. And it's pretty much the premier fusion research detector anywhere in the world at this point in time. But although we operate it, the users are spread all over the place. We have over 700 research users from pretty much all major countries around the world. So we are a truly international collaboration. So, back to CGYRO, because that's what I would talk mostly about. So CGYRO is an Eulerian gyrokinetic solver, so whoever knows anything about fusion will know what this means. Everybody else is the name. And it's designed and optimized for collisional electromagnetic and multi-scale fusion plasma simulation, and is based on an older code, GYRO, which was also developed by General Atomics. But this is pretty much a rewrite of that code, so that it's suitable for next generation computational system that require high levels of parallel concurrency, which means multi-node, multi-core, GPU offload, and definitely optimized for petascale class systems. So why CGYRO? Well, CGYRO is production quality code. It has hundreds of users that use it all the time, and they use it on leadership systems. And Summit is the next big one, so we want to make sure that we can run there, because people are eager to get there because of the scale we're getting there. It's heavy user resources. We have logged millions of node hours on both Titan and Core. So the computational efficiency is very important. We don't want to waste resources. We want to go as fast as possible. And we also benchmark it on many, many systems, so we can make comparison between these different architectures very easily. I was hoping to have a paper out about this out by now, but didn't get to it. So hopefully it's sometime in the future. But why do we care about fusion simulation? Well, it's needed if you want to run a fusion plasma apparatus. Both current ones, which is a study one where we try new stuff in order to see how we can safely increase the power output without blowing up the machine, and future ones, this is ITER here in Europe, which is much bigger. So this is the person, this is the detector. It's really, really big, and you probably cannot see it, but it's a truly international collaboration. Various pieces have been contributed from various different places around the world, and I think General Atomics provides a set solenoid and some other pieces apart from software. So back to CGYRO, it is written in Fortran, modern Fortran, not 77 from your grandpa's. It uses MPI to split the problem across many independent processes, and then inside the processes we use OpenMP and OpenACC, and we usually on GPU system we use both at the time. So wherever is code that needs to run on the CPU, it's OpenMP. Whatever code needs to run on the GPU, uses OpenACC. Of course, if you're only on the CPU, it's OpenMP only. But, yeah, we have both, which gets tricky sometimes, getting the two to play nicely with each other. Just a picture of why we can scale very nicely. This is how we split the problem. So we have the multi-scale mesh, and then within each of this mesh, you have the ion-scale mesh, and within each of these boxes, you have the velocity space mesh. I will not go in details what that means, but you can see that we have a lot of parallelism, and it's all nice and independent for large parts. Then you need to do synchronization, but it's very homogeneous. It's not like the talk we heard this morning with big imbalances. This goes all along together, and if it was all on a shared memory machine, you could really go completely independent. When you go across nodes, we have a lot of MPI communication, and that actually can be a problem for large machines. So we need really good networking for our application. So that's why we care about leadership of systems, just a bunch of loosely coupled nodes. Unlike the machines this morning, which were lots of independent 32, I was just helping a user that needs at least 4,000 nodes to actually run it. Anything less, I need it out of memory. So we really need big machines. It's not that we just need the power. It's really need to be big with good networking between them. So for the purpose of the benchmarking, it's good to understand that CGYRO is really split in 3 logical kernels. We have the streaming kernel, the nonlinear kernel, and the combination of field and collisional kernels, which will, for simplicity, just call the collisional kernels for the rest of the talk. And a simulation is essentially a lot of steps that do these 3 in sequence and start again with a lot of communication between them, because we need to essentially keep a big picture in mind, even though we operate on a small subproblem. In the sense that we essentially use a 2-dimensional MPI communication strategy. There is some additional code needed for monitoring error handling, but it's cheap, so it will be bundled in the other category because it really doesn't matter too much. A couple of words about 2 of the kernels. The NL kernel is typically the most expensive one, and this is by design because we implement a lot of our logic as a series of 2D FFT transforms, and there are good libraries for this, so we don't have to write them, and we delegate the work in the libraries, so we can use whatever optimizations others provide to get most of the speed. And for the collisional kernel comes with 2 different versions. we have a high fidelity version, which uses a large amount of memory and is quite expensive. Typically, the memory throughput heavy, but it just takes a long time. And a simplified version, which is much cheaper, uses just a fraction of the memory and is typically flops bound. It's just not so much memory and way less calculation. But it's still good enough for some of the simulations. So the really expensive simulations usually end up using this, else you spend way too, the simulation becomes way too expensive. So since we are talking about GPUs, a word on what is our GPU enableness. We ported CGYRO to Titan several years ago, pretty much when it came out, and we used OpenACC for that, and we basically haven't changed it since. Although we have ran on Bitsdane, but it really didn't need any changes to run there. And one thing that is important in this context is that MPI communications are not GPU aware. There was no GPU direct at that point, so we didn't even try to do that. So, which means that anytime you use a GPU, you need to bring it back for MPI. We do a lot of MPI, so pretty much you have to do computation, bring it back, do the MPI, put it back in the GPU, and so on. And this sort of influenced how we went about GPUifying the various kernels. The NL kernel is all on the GPU, mostly because we use CUDA FFT, and whatever else glue we have, we use OpenACC, relatively straightforward. The STR kernel is only partially GPU enabled. We saw what was the most compute intensive part, put it on the GPU, and left a big chunk that still on the CPU, because moving the memory from CPU to GPU and back is more expensive to actually doing the calculation on the CPU to start with. At least on Titan. And while the collisional kernel was always CPU only, the expensive one just uses too much memory, and the cheap one we said, well, it's so cheap, we will not even bother trying to do that. Now, in order to benchmark a tool like this, you need to decide what input parameters you will use, because CGYRO can be used for tiny simulations which are good enough to simulate the core, or the big simulation that use the 4,000 nodes of the user I just told you about, which are necessary to accurately describe the pedestrian region, and you can do anything in between. Unfortunately, we had just a couple of nodes, so we had to stick with the small ones. It would just not fit in the hardware we have available. And just since I was talking about various pieces of the plasma, this is what the plasma cross-section looks like, and there you have an example of simulation. As you go from the core to the outside, the core is the really hot one, but it's quite homogeneous. As you go farther away, there are various turbulences going on, and when you go really close to the edge, all kind of weird stuff happen, because you have very steep gradients in both electrical and magnetic fields. Lines start to open, and it's really, you really need to very fine-grained mesh in order to figure out what is going here. But for the core, coarse-grained mesh gives a good enough representation. By the way, this is pretty much this kind of simulation. So the two specific test cases that we have picked, and I will use these names later in the talk, but they are also part of the GitHub repository. So if you want to download the code and run it, you can actually run exactly the same test. They are committed. The NL01 test case is representative of plasma core simulation and includes the full high-fidelity collisional kernel. And the SH02 is pretty much the biggest one we could run on available hardware. It's still not good enough for going to the pedestal, but it's as big as we could go. And we use a simplified fast collisional kernel you would usually use in the pedestrian region, pedestal region, simply because we cannot afford to run the full one. It's too expensive. So this is for the background, and now to the actual porting and benchmarking part. But first, what was the hardware we had? We bought essentially IBM AC922 servers. which had inside two 16-core Power 9 CPUs at 3.5 gigahertz, and four Volta GPUs with NVLink. That's the only thing that IBM would sell us, pretty much. We have half a terabyte of CPU and 4 times 16 gigabytes of GPU RAM, and really the limiting factor is this. We never get even close to this. And we use Red Hat Enterprise Linux 7.4 as an OS, in case you're wondering. We bought and deployed this in early 2018, pretty much at the earliest point in time we could get our hands on. And just for clarification, I will refer to this node as GA Summit in the rest of the talk, so I don't have to say the Power 9 node, so forth. It's GA Summit. So, porting. Now, we never built anything on Power 9, but CGYRO is a standard Fortran application, can be compiled pretty much with any Fortran compiler, but for all GPU-enabled systems, we have always used PGI. So we said, okay, we'll go PGI here too. It supports Power 9, it supports Voltas. That should make it easy. So we went ahead, installed the PGI compiler, and it comes with CUDA, MPI, and BLAST out of the box. So we used the PGI provided ones, so we didn't really need anything apart from the OS on the machine. And it was very straightforward, although it did hit minor licensing hiccup. Essentially, we already have PGI for Intel, but the licensing server doesn't work with the Power 9 version. Whatever, they gave us node license and we were okay. We also installed and compiled the FFTW. Although we don't strictly need it for the GPU version, we wanted to benchmark how the Power 9 CPUs work, and we need for that. And PGI actually provides cut and paste instructions, so easy. It was trivial. And now it was time to build. We used the same recipe we used for other GPU systems like Titan or Pittstain. And surprise, surprise, it just worked. So the build succeeded the first try. All the regression tests just worked out of the box. And we said, okay, we were planning to spend a month doing this.
You're making Michael Wolf happy.
It's 4 p.m. So what we were doing for the other 29 days. So yes, it was really easy. It works out of the box. It doesn't feel like any other machine with GPUs. It just works. So the Power 9 ecosystem is actually pretty mature at this point. So we said, let's go benchmark, and our main goal was to see how this node performs compared to other machines that we had access. But first we need to understand what is the ideal way to run on this node. We don't have a batch system, but everything else that will happen on the real summit. So the two things that really were interesting to us is what do we do about hyperthreading, and what is the difference between CPU and GPU version. So as you probably know, you have 4 hardware threads per core on the Power 9. So we took the largest of the test cases, which is more realistic, and decided to use all the cores, which means 2 times 16, but just vary a number of OpenMP threads so that we would have between 32 and 128 total threads in the system. And here are the results. Well, the hyperthreading is really a wash for us. It doesn't matter if we would use 1, 2, or 4 hyperthreads per core. The results are almost within the statistical error, which is about 5%. So, and different kernels behave differently. For some, like the Enel kernel, it's actually, you get a little bit of improvement if you use hyperthreads. But for other kernels, it's actually worse. So, at the end of the day, it's a wash. We decided to stick with 2 because it gave us the best performance here, but we think it would not make much of a difference to stick with 1 or 4 for all the tests. And yeah, I will have these summary slides all over the place. I uploaded the doc on SlideShare if you want to Google it, so you can read it offline. Now, that was nice, but we really want to use the Volta GPUs because at least on paper, pretty much 95% of the flops are coming from there. So yeah, Power 9 is fine, but really on paper, Volta is doing all the work. However, CGYRO is only partially GPU enabled, so we wanted to see what was the real impact on using the Voltas on this machine. So here are the numbers. Essentially, we get a nice 3x, total 3x speed up by using the 4 GPUs, but on total time, but it affects very differently the various kernels. The NL kernel, which was the most expensive one, it becomes essentially the cheapest one, because it uses good FFT, and yeah, we get a 9x speed up. Our SDR kernel, which is partially GPU enabled, it gets a modest 2x speed up, but it's still nice. And the CPU only one, well, it's CPU only, so it gets no speed up at all. So from being the smallest one, it became the big one. So it's now the limiting factor. And for the smaller NL01 test case, it's even worse, because this is much bigger. So while the others shrink nicely, it's now half of all the runtime. So we didn't get even a 2x speed up in total time. So lesson number 1, work on getting this on the GPU. That's pretty much what it says here. So now we know where we stand on the single node. Let's see how it compares with nodes from other machines that we have access to. And essentially, we picked 2 GPU or hybrid, if you want, systems: PISDAINT, CSCS, and Titan or ANL. PISDAINT is a Haswell plus Pascal infrastructure. Titan is an older Opteron with coupler, plus 2 CPU-only systems. Cori, which the Xeon Phi's, and Stampede 2, although we had access to Phi's 2, we decided to just look at the Skylights, so to have a comparison with another architecture. So first, let's just see how well the Power 9 CPUs behave, especially since it's an OpenPOWER. I thought it was interesting. So with benchmark single nodes across all the various options, and we just stuck with the new CPU systems. No point in benchmark the older Haswell or Opterons on Titan and PISDAINT. One thing to notice is that we use different libraries and compilers on different machines, and the reason being is that we wanted to use what we would really use in production. So these are the Intel plus FFTW is what you get on Cori. Intel Fortran with MKL is what you get on Skylake. And the difference is that this is a Cray machine and makes it a real pain in the neck to try to use MKL, while this is a Dell machine and doesn't have the Cray wrappers, so MKL is what they suggest. As I said, we use PGI everywhere where we use GPU also, so we didn't want to try to do something different. So here are the results for the big test. As you can see, we get pretty much the same timing for our Power 9 base node and for the KNL base node. So 2 Power 9 CPUs are equivalent to the single KNL. So node by node, it's pretty much a wash. The Skylakes are much faster, but if you do the math, per core, it's pretty much the same. This is just have 16 nodes, 16 cores per node. This has per CPU. This has 24. So if you do the math, core by core, pretty much a wash on the core by core version. And you see the things scale pretty much the same across all the kernels. It's not that just one kernel was particularly bad. It's pretty much within a little bit of variation, but not much across all the kernels. And this holds true for the smaller NL1 case too. The numbers are slightly different, but the proportion, if you look just at the graph, you see it's in the same ballpark. So, yeah, this is what I was saying. So the 2 Power 9 CPUs are pretty much the same as the KNL. But this is just for the CPUs. What we really care about from a scientific point of view is how the whole node will behave with everything that you have on it, because we will never just not use the GPUs if they are there. And here we will benchmark against both CPU and hybrid systems. One slight detail is here that the SH02 benchmark doesn't fit on a single node on most of the other machines. It just uses too much memory. It fits perfectly in the 4 GPUs we have on our machine, but it doesn't fit in a single GPU that all the others have. So we'll have to have some different metrics, and we'll see what it is. And again, for the compilers and libraries, it's Intel on Core and Stampede, and PGI plus CUDA FFT on all the hybrid systems. So at least all the hybrid systems are the equal level playing field. So here are the results. Here the benchmark is slightly different. I try to pick the number of nodes that give me approximately the same amount of runtime. Since I don't have 4 Power 9 nodes in-house to try, and I think it would not even run on 4 nodes of Titan. Simply, the memory was not enough. So you see that a single JS Summit node is pretty much equivalent to 4 pit-stained nodes, between 8 and 10 pit-stained nodes, depending how much you count the network overhead. By the way, the other includes network I/O and some additional monitoring code, but it's mostly networking. It's about 3 times the KNL, and I have to, all our tests need to be run in powers of 2, so I couldn't run it at 3x. And it's pretty much the same as the Skylake. So after we take everything into account, this node is about twice as fast as the Skylake. And here is a different view, same picture as before, but trying to scale the numbers instead of measurements. This is just an estimate. If you linearly scale so that all machines would be on 8 nodes, you see 4, 8, 3, and 2. Oh, and by the way, it may be worth looking at the various kernels where the performance gain comes from. So the ML one is great. When you go from CPU to GPU, you get a huge speed bump. For SDR, even though it is partially on the GPU, the inter-CPUs still rule. And it's the same for the collision, which is CPU only, of course. And here you also see that pit-stained and Titan get significantly ahead because just have more CPUs. For the NL01, this actually fit on a single node on all the machines. So we can actually have a single node-by-node comparison. And you see it's a little less pronounced because of the heavy impact of the collisional kernel, but this is still the fastest node in the bunch, and the Skylake is very close. And you get a 3x speed up approximately over pit-stained, about 6x over Titan, but 1.5 for the Phi, and it's about to wash for the Skylake. And again, the NL kernel is great, but this has become the dominating part. So, and Skylake just fly there. One of the reviewers asked why is that, I don't know, 19 benchmarking. So Skylake just seems to take better advantage of the hardware.
Excuse me.
Yeah.
Did you turn on the AVX 512? AVX, I mean the AVX 512 instruction set.
On the Skylake?
On Skylake, yeah.
Oh, yeah, it's on, of course, yeah. Yeah, we use maximum optimization. We essentially use OFast on all the machines, whatever it means. We usually don't try to optimize too much. It's OFast, and usually the compiler does a pretty decent job on all of them. Or whatever is the equivalent for different compilers. So as I said, it's these nodes fly. It's really the fastest we ever saw, and On the more realistic SH02 case, it's about 10 times tight and 4 times speed stain and 2 times stampede 2 and probably 3 times KNL. But we do see that the CPU-only SDR kernel is limiting how much we can go. So these are the numbers I have in the paper. So let me summarize first, and then I have something that is not in the paper, actually. So we bought and deployed the PowerMine plus Volta nodes to prepare for Summit. And since CGYRO is our premium feature code, that was the one that we wanted to get there as soon as possible. And the porting itself was a breeze. Really couldn't be happier about that. For the Power 9, well, first lesson, hyperthreading, is there or it's not there, doesn't make any difference for us. Compared with other CPUs, node by node, it's about as fast as Xeon Phi, and core by core, about as fast as a Skylake, at least the ones that are deployed on Stampede 2. And there is a very huge reliance on the GPU. We actually didn't appreciate it until we saw it. Although looking at the theoretical numbers, we should have imagined it. But also from the benchmark, yeah, wherever GPUs are used, they are fast. And this makes this node the fastest we ever benchmarked. And the lessons learned from this exercise were, one, we think we can run on Summit, it should just work. So this is good news. But the CPU-only code will likely be a bottleneck. So we should do something about it if we want to run efficiently when Summit comes online. So this is a part of the paper. And what happened after we learned the lessons. So seeing that we were not running as fast as we could with the existing code, we went ahead and said, okay, let's try to put everything on the GPU that we can. And by now, everything is on the GPU, at least the main kernels. All the various debugging, monitoring stuff, it's still CPU only because it's peanuts. And we also implemented GPU Direct. And I think everybody here knows that this is MPI that uses directly the GPU memory. Word of warning, still preliminary results, still making sure everything works as it should, and don't take it with a little bit, a grain of salt. But here is the result. First, using everything in the GPU used more GPU memory, so the big case doesn't fit on our 4 GPUs anymore. So we had to split it at least 2 nodes.
Well, why was that? Say that again, please.
Well, when we put everything on the GPU, we started to use more GPU memory.
Okay.
So the 64 gigs across the 4 GPUs is not enough anymore in this case. Luckily, we bought two nodes, so we could actually test it with 2 nodes. They're configured with InfiniBand. I'm not exactly sure what kind of InfiniBand. It was not meant to be really high-end networking. Good enough for MPI, but probably some real Summit and better networking.
Did you try running out of the CPU memory?
No, we don't. We do explicit memory movement. We don't use managed memory or something like that. So it just crashes. It says malloc, CUDA malloc failed. Boom. So no, we are not trying. Also because it's not. We don't really care about running a small number of nodes. We try to push as far out as we can.
Okay.
Yeah, but there is a large model support available, right? People say that if you turn on that, you'll get a better performance.
No, the problem is we just don't have enough memory. So we need more than 64 gigs of memory, and that's all you have on the GPU.
No, I'm talking about the CPU memory. I mean, the general systems memory.
That shouldn't really matter much because right now I put pretty much everything in the GPU.
Okay.
The problem is just there is not enough memory. So I have to split it across 2 nodes. So the benchmark now is across 2 nodes. But you see, it's actually good. We get 3x speed up, same hardware, just a little bit optimized code. And this got, it's probably not 50, but it's probably 30. I probably should include the first digit afterwards. But you can see even the NL kernel got the 3x speed up. And that tells us that really, 2/3 of the time was spent moving memory back and forth. Because the code didn't really change much. The compute is pretty much the same. But since we don't have to move the memory in and out of the GPU for MPI, automatically you get 3x speed up. It was more than we expected. And it's the same for the SDR kernel. An interesting thing is that the network times actually went down. We were a little bit worried keeping the memory in the GPU for MPI, but it actually it's pretty much half of what is here. So even the inter-process communication went faster using the GPU direct. Incredibly, the numbers look almost the same for the small one. Again, the 3x speed up. Even though this was so big and become much smaller, everything improved pretty much by the same amount. Actually, this improved less than on the other thing. We didn't think that this could be possible, but it actually went extremely fast. So even though this looks bigger here and smaller here, it doesn't really make a lot of a difference. So it's 3x on both cases. The network time stayed about the same, but very happy about it. Now, we wanted to see how these improvements behave on the other machines, and I guess IBM has a reason to go with today, because when you retest this on PITSDaint, which is an Intel plus Pascal over PCIe, well, the compute numbers are as good as they were before, the networking just explodes. So using MPI direct there is a no-no. While on the 2 nodes, it's still better than before. As we start scaling up with the number of nodes, it just keeps growing and growing and growing and growing. So after, I think already at 8 nodes, we actually slower if you use GPU direct and plus the new GPU changes, then just use the old code that ran mostly on the CPU. So the Power 9 architecture actually helps a lot. If you want to use MPI direct, now it's finally usable. On PITSDaint, really it's not. At least in the setup we have. Maybe I'm doing something stupid, but it's the same compiler, same everything. I think we enabled everything that was to be enabled. The MPI libraries are different. Maybe just Cray doesn't know how to write the MPI because we are using their MPI versus Open MPI comes with PGI on our machine. But yeah, just taking stuff as we always did it, this is what we observed. So in summary, we think we are ready for Summit. We have an allocation there. We really would like to see at least a benchmark of this on more than 2 nodes. But 2 nodes is all we have in the lab, and Summit seems to be 6 months away. But we did what we can. I think we're ready. The moment you let us in, we should be able to run. And just a final PR slide saying, if you like what we do, we like to collaborate, just contact me. So, questions?